Alright, so this is example 5.1 from the text, and you can see it consists of this device for clamping a flat workpiece in a machine tool, and so that device is this sort of curved piece, and it's telling you that you need a 200 Newton clamping force at point C here, and that also there's no friction at point C, so that means that there's no, I guess, X component of the force there. There's only going to be a Y component, and that Y component needs to be 200 newtons. And it's asking them for what is the horizontal force that has to be applied at A in order to get that, and then also what's the reaction force that's applied at point B. So go ahead and give that a shot, and then come back, and we will go through this problem together. Alright, so the way I'm going to do this problem is initially I'll define the coordinates. So you can see there's 4 points, A, B, C, and D. I'll define the coordinates of those points. And B and D together is going to give me the reaction, or the position vector RBD, and that's going to define the direction that that reaction force at point B has to be applied. So I don't know the magnitude, but I know the direction. So there's one unknown there. I know exactly the force applied at C, and then I don't know either the X or the Y component of the force that's going to be applied at A. So that's 3 unknowns. But I have 3 equilibrium equations, which are that the sum of the forces in the X and the Y have to be 0, and then that the sum of the moments around any point have to be 0. In this case, we'll take the moments around A. So that's how we'll solve the problem. And we'll go ahead and derive the governing equations before we open up E's and try to solve them there. So first we'll define the position vector RBD, which is just the coordinate to point D minus B. And you can see that's going to give me that direction, FBD. So here FB is going to be the magnitude of that force multiplied by the unit vector in that direction, RBD. And then I have a force equilibrium equation, which is just the force A plus B plus C has to be equal to 0, and that's a vector. That's a 2D vector equation, so that's really 2 equations, one for the X and one for the Y components of these forces. And then finally I have a moment equilibrium equation, and that requires that the sum of the moments around any point on the clamp be 0, and here we're going to take A, so that means that then RAB cross FB, so that's the moment produced by this FB, the reaction at B, plus RAC cross FC, so that's the moment produced by the clamping force. Those two have to sum to 0, and that's a scalar equation in 2 dimensions. That's a scalar equation, and the RAB and RAC are position vectors defined by the coordinates. So that should be enough equations and enough unknowns, so we can go ahead and open E's and try to solve the problem. So the first thing I'm going to do is define 4 2D vectors, so dollar vector 2D, and these correspond to the coordinates, so A, B, C, and D. And in order to define the coordinates, I need a coordinate system, and it really doesn't matter what coordinate system. I'm going to choose a coordinate system where the origin is the X location of point A and the Y location of point D. So basically everything will be positive away from those points. And so with that choice, then you can see that I can use vector assign to go ahead and define those coordinates. And then the position vector RBD, that's just D minus B, so I'll define that to be a 2D vector as well. The force at C, so this is the clamping force, is known, so that's vector assign, and it's got no component in the X direction but 200 newtons in the Y direction, so vertically up, so that's easy. And then the vector, the force applied at point B is some magnitude of that force, and then I know the direction, so it's multiplied by the position vector RBD divided by its magnitude, which is the unit vector in that direction. And now I'll go ahead and enter my equilibrium equations. So the first one is FA plus FB plus FC is equal to 0, and this is of course not just scalar 0 but vector zeros. And then I'll enter the moment equilibrium equation. So RAB is B minus A, and that defines the position vector from point A to point B. RAC is C minus A, so that's from A to C. So the vector cross of RAB and force B plus the vector cross of RAC and force C has to be equal to 0. And again, in 2 dimensions, this is a scalar equation. So I should have enough equations and enough unknowns. I can go ahead and solve. And if I do, I get that the magnitude of that reaction force is 581.6 newtons, and that FA, so this is the force applied at A, has a horizontal component of 513.2, and it's got a vertical reaction of the roller against the wall of 73.68 newtons. So that's the problem. We can do some other things with it now that we've programmed it. Now the first thing I'm going to do is make a 2D vector plot, which is a force polygon. So I'm going to have each force vector start at the head of the previous force vector, and just make sure that the forces sum to 0. So the vector sum of these is 0, which means that the polygon closes in on itself. So I'll use the dollar vector plot, in this case vector plot 2D directive. I'll call the plot force polygon, and I'm going to plot the 3 forces. So the first one is FA. I'll start it at 0. I'll make it red. The second one is FB. I want to start this at the head of FA, so that's exclamation point, means start this at the head of the previously plotted vector. I'll make that red as well. And then FC, same thing. So I'll start this at the force of at the head of FB. So exclamation point red. And if I solve now, you can see I have this force polygon, and visually I can see that at least my forces add up to 0. So force equilibrium equation is being enforced correctly. The other thing I can do is start to vary parts of the design. So one thing I could do here is vary the location of point B and see how does that affect the performance of the clamp. And in this case, we'll take the performance of the clamp to be the required force in the x direction that has to be applied at point A, so FAX. So I'm going to create a 3D plot. I'll go ahead and just comment out the coordinates for point B. So that gives me actually 2 free parameters, right, bx and by. And I'm going to go ahead and make a parametric table that includes bx and by and also fax. And we'll vary bx from 40 millimeters to 125 millimeters, so that's a pretty big span of x locations, and from 0 to 32 millimeters for by. So 40 to 125, I'm going to do that every 10 rows, and same thing for by, but I'll apply the pattern every 10 rows. So I get a complete sort of grid of these different coordinates, and I'll solve the table, and then once I solve it, I can make various types of 3D plots. So here I'm going to make a contour plot, and you can see it's kind of interesting that if I want to require the smallest force at point A in the x direction, I would put that coordinate B, all the way up here, sort of at the upper left corner of the parameter space that I investigated. And then as you go down towards the bottom, there's a place where you can actually maximize that force. I'll also make a surface plot just because I think surface plots are cool, and that's shown here, and it shows the same thing but maybe in a little bit more interesting way. You can spin the surface plot around and look at the results.